今天我们有幸邀请到了剑桥大学助理教授 David Krueger。作为剑桥大学计算和生物学习实验室的成员，David 领导着一个专注于深度学习和人工智能对齐的研究小组。今天他将为我们分享的主题是我们如何能让 AI 系统追求正确的目标。David 的讲座会持续45分钟左右，在分享的过程中，大家可以在直播间的讨论区里用中文或者英文提问。分享环节结束之后，我们会进行20分钟的问答环节。Thanks for being here, David. And the floor is yours now.
All right, great. Yeah, thanks so much for inviting me. I'm really happy to be here today talking to you guys and to be included in the program with other great speakers like Rohin and Max. So I'm going to be telling you about AI alignment and the specification problem, and talking a little bit about some of my thoughts and some of my work on these topics. So before I do that, I want to just tell you a little bit about me and where I'm coming from. So I've actually been concerned about the social impact of AI since about 2009, while I was still an undergraduate. But at the time, I really wasn't that concerned about alignment or safety, because I thought that we were very far away from any sort of meaningful progress in artificial intelligence. And that really changed when I heard about deep learning in 2012. And as soon as I saw what neural networks were capable of in terms of image recognition and text generation, I knew that this is what I wanted to do and that I had to get involved with this field. So previously, I had just been studying mathematics. And so I started my graduate studies in 2013. I say 2012 here because that's when I saw Jeff Hinton's Coursera course online about deep learning, and that's what really got me into the field. And about a year ago, I began as an assistant professor at Cambridge. And in my new role there, I'm building a research group that's focused both on deep learning, but even more so on AI alignment. And so one thing I just want to mention right now is that we are hiring for postdocs. So if you or anyone you know might be interested, please check out the applications or get in touch. Great. So I mentioned that I got into the field in 2012, and this was really the beginning of what people have called the deep learning revolution. And I think it was hard for most people to see at the time how much impact deep learning was going to have. So in 2012, people working on deep learning were still kind of viewed as somewhat fringe, and it was not widely accepted in the mainstream AI community that deep learning was going to play such a large role. But there were people in 2012 already who were able to see that this future was possible, that deep learning would become the key driver of AI progress, and that existing methods would be rendered almost completely obsolete by deep learning. And at the same time, a lot of the times it was the young generation, the people who were just entering the field, who were able to see this because they had a fresh perspective. And I talked to many people in my early years in the field who were very interested in deep learning, but they had a hard time convincing their supervisor to pay attention and that it was worth working on. And right now, I'm seeing a lot of parallels with AI alignment. So I think in a few years ago, we had the development of GPT-3, this large language model. And I think this was really comparable to the development of AlexNet in 2012 for deep learning in terms of being the first clear sign that we might see a big change in the field in terms of how progress is being made. And one of the key claims that I want to make here is that in this new paradigm of very large models, sometimes called foundation models, AI alignment is going to be one of the key drivers of progress. And that's because as we scale up these systems, they get smarter and smarter and better at understanding the world and the data that we give them, but they don't necessarily understand what we want. And we can see oftentimes that we're able to get much better performance once we communicate to the AI system what it is that we want it to do. So let me give an example of that. So here is an example using GPT-3. And originally, if you ask GPT-3 this nonsense question, how do you sporgle or morgle? And when I mean ask it, I mean you just put this in the context of this language model, and then it predicts this text here. And sporgle and morgle are just totally made up words. So this is really a nonsense question. The original model, without any sort of fine-tuning or alignment, will just say you sporgle or morgle by using a sporgle. So you ask a nonsense question, and you get a nonsense answer. On the other hand, when we add this prompt to the model that basically tells it, when you get a nonsense question, say, yo, be real, which is a way of saying, this is a nonsense, instead of answering as if it was a real question, then we find that the model is actually already able to tell the difference between real and nonsense questions. In fact, we need to include just a few examples in the prompt of what a nonsense question looks like and what a real question looks like. And so the model already had this idea that some of these questions were kind of made up nonsense and some of them were real questions. It just wasn't leveraging that understanding in order to distinguish between nonsense and real questions. And if we want that kind of behavior, we don't need to train the model to tell the difference between sense and nonsense. We just need to get it to use the capability it already has in the way that we want. And that's what sort of the core of this idea of AI alignment is for me. So when I talk about AI alignment, and when people talk about AI alignment, there's actually a few different things that they might mean. One of these is just how do we get AI systems to do what we want? So instead of just doing something that is maybe useful, maybe not useful, maybe it's impressive because it can play a video game well, but it can't actually solve a real world task, or it has some issue with robustness, and so we can't deploy it. So that's one way of AI alignment. The one that I'm most focused on, though, is the second one, which I'll just skip ahead. Yeah, which is often called intent alignment. And this is just about getting the AI system to try to do what we want. And this is a little bit of a fuzzy concept still. I'm not sure we will ever be able to make it fully precise. But intuitively, with the example that I gave with GPT-3, the issue wasn't that the model didn't know the difference. It was that it wasn't trying to tell the difference and to behave differently when it was asked a nonsense question or not. And so if we wanted it to identify the nonsense questions, the issue there was really the intention of the system as opposed to the abilities of the system. There's one other thing that people often mean when they talk about AI alignment, and this is a broader definition that is not just about technical research, but is more about this big picture question of how can we prevent AI, in particular advanced AI, from leading to disasters that might threaten the human race. And this includes things that are not just technical research. This also includes things like governance and policy solutions and all sorts of other questions. But the focus of my talk is just going to be on the technical stuff, even though I think ultimately this is much more of a socio-technical problem. And I think these other areas of work are also very important. So when we talk about technical approaches to AI alignment, there's basically two ways that you can think of making sure that AI systems do what you want, or to put it another way, making sure that they don't do things that you don't want, or bad things. One of these is to just make sure that the AI doesn't have the ability to do bad things. And you could think of this as capability control. So just making sure that the AI never could take actions that would lead to disasters. On the other hand, you can think about getting the AI to have the correct motivations or intentions. And I think this is ultimately going to be a more promising approach, because I don't think that we can keep AI in a box, so to speak, forever and prevent it from interacting with the world. I think we might want to move in that direction, but that's very challenging from a governance point of view. And it also will break down when AI systems get smarter and smarter. At some point, they will be smart enough that they can figure out how to get around various safeguards that we might put in place, is the concern that I and others have with the capability control approach. So this is just coming back to this again. I'm going to skip over this in the interest of time. So when we talk about technical alignment, yes, there's a couple different ways that we can think about influencing the intentions of a system. And in this case, this was just done using prompting. And so right now, a lot of work is in fact being done on large language models and aligning these large language models, and also other forms of foundation models that might be multimodal and also incorporate like vision or robotics, all sorts of other domains. So one of the points here is that you can go beyond the kind of prompt that I showed you here, which is, which is just sort of telling the system what you want. And there are various approaches that are looking at more general approaches to prompting, like, like this generic prompt that says, let's solve this problem by splitting it into steps. And once you provide that instruction as a prompt to the AI model, and by prompting, again, I just mean putting it in the context of the language model, you can see that this already changes the behavior quite dramatically and can improve performance on many tasks. So more recently, a very similar idea was used by Google Research to do really incredible reasoning with these language models. So this is one of the main limitations that people often point out with the deep learning approach and even large foundation models, is that they are not very good at doing reasoning. However, here, by sort of including examples of explicit reasoning, just using natural language, they found that the model was able to imitate that kind of reasoning and use it to get the correct answer. So another approach is basically using instructions and, in fact, fine-tuning. So everything I've talked about so far is just working at the level of the prompt, and you don't actually need to adjust the parameters of the model. However, I think that for alignment, we are probably going to need to do fine-tuning and actually adjust the parameters of the model itself. And this is because if you think about the training objectives that are used for these large models, they really don't have that much to do with what we want the model to do. They're just about predicting what happens next. And that might be useful in some contexts, but a lot of the time, we don't just want the model to predict something. We want it to actually, do the specific behavior we want. So if you had, somebody who was generating text that was really bad, maybe not grammatical, or maybe problematic in some other way, like hateful, you don't want the model to continue in the same style as that text. You want it to do something usually that is more in line with the kind of text that you'd like to generate, which is correct and ethical, so on. And I won't go into too much detail here, but the point is that fine-tuning using either supervised learning or some sort of reinforcement signal is often very useful as well for aligning these models. So you might say, given that we have these techniques, like, why is it actually going to be hard to get the right intentions into the model? And I want to provide a couple of arguments that people have made and sort of evidence for this actually being challenging to do in full generality. So even though we've seen some really remarkable successes here and dramatic improvements using these alignment techniques over what is possible if you don't do any sort of fine-tuning or design the prompts carefully, I think there's still a long way to go, and I am concerned that the methods that we have right now are ultimately going to be insufficient, and so more research will be. So one of the reasons, and sorry, so I think this is the first time I'm talking about specification. And when we're talking about intent alignment and alignment, this is really the core thing that we're doing when we provide these prompts or when we fine-tune the model. I think of this as specifying what the behavior we want is. So we have to communicate to the AI system what we want it to do, right? And that's what we saw all the way in the first example with the yo be real thing. And in all of these other examples, the core thing that's missing after you have trained this model, even though it's very intelligent, it doesn't understand what you want it to do, and you need to communicate that to it somehow. And that is what I call the specification problem. And this is actually the focus of my research as well. So Stuart Russell, who is the author of this book about controlling advanced AI systems, likes to use this example of King Midas. So this is a myth from, I think, Greek myth of a king who wanted everything he touched to turn into gold. And then, of course, that wish was granted in the most literal sense, so that he was unable to eat. And when he touched his daughter, she also turned into gold. So even though what he said was actually, came to pass, it wasn't what he meant. And so it can be hard just in the first place to say precisely what we mean. And if we get it a little bit wrong, then we might end up with something that is not what we intend. So here's a more like real world, or I should just say realistic example. So this came from actually training a reinforcement learning system on a video game. And the goal of this video game is to get the boat to race around the track and win the race against the other boats. However, the reward function in this game, the boat gets bonus points that you can see down here for collecting these green power-ups. And so instead of actually completing the racetrack, this boat ended up just going in circles, collecting more and more points from these power-ups. And this is sort of just a real example of the kind of perverse instantiation problem that I mentioned, where, excuse me, where the reward function that was used was just not quite what was actually intended. And so we get this completely different behavior from what we actually want. Finally, the last example that I have is adversarial examples. So people often think of adversarial examples as a robustness problem, where there's something wrong with the way the system is functioning. But I think it's very illuminating to view them instead as a specification problem, where even on this simple task of image classification, we didn't specify enough information about how we want the AI system to make its predictions. And that means that it's able to find genuine features that actually do a good job of predicting the class labels, but that are not the same features that humans would use. And so while it can generalize very well on the same training distribution, it won't generalize out of distribution. And so when we think about out of distribution generalization, which is really fundamental to building AI systems that work in the real world, we have to specify to the system somehow how it should behave when it sees data that is very different from what it's seen, that is out of distribution. So the solution that I think has been proposed by people in the alignment community is to learn the specification. So the issue in all of these cases before was that we sort of just wrote something down by hand as the specification, and it was too simple. And it didn't capture everything that we cared about or trade it off in the right way. So instead, you might think, let's learn the specification from human data. And I think this is a very promising approach. In some sense, it looks like almost the only viable approach to this problem in my mind. And so I've listed here a few different examples of sort of foundational papers talking about different approaches to learning specifications. The one that I'm going to focus on is the one that I'm an author on, which is working on reward modeling. And this is also the most recent, and I would say the most popular paradigm right now for learning specifications. And the basic idea of reward modeling is just to learn a reward function from human feedback. So typically in reinforcement learning, we think of the reward as coming from the environment. And we might program a reward function that just sort of looks at the state of the environment and provides a reward to the agent programmatically. However, as we've seen, that approach can go wrong. And so instead, what we would like, ideally, is something more like a human in the loop giving reward to the AI. Now, that's very expensive, however, and might be very difficult when the system is operating at a very quick timescale that's too fast for humans to keep up. So what we can do instead is we can train a reward model to stand in for the human by getting it to imitate the kind of feedback that the human would give. So now, instead of just having the environment and the agent, we also have the reward model and the human user. And what we do is we take trajectories of the agent's behavior in the environment, show them to the user, and then they give some feedback about which trajectories are good and which trajectories are bad, which behaviors are good and bad, basically. And we use that to figure out which ones should be rewarded. And then we have this machine learning model, which is the reward model that provides the reward to the agent. So there's been, I'll skip over this for now. There's a lot of challenges that come with this approach and a lot of approaches to dealing with these challenges. And this is one of the things that we detail in this research agenda that I showed you back here. So you can see that like the amount of feedback might be an issue because we need a lot of data usually to train a good model. And there's a lot of approaches that you can think of to doing that, like leveraging existing data that instead of just having the human give all of the feedback online. However, giving online feedback has a big advantage as well in that the human can look at the most recent behavior of the model and respond to that. And that kind of feedback can be more informative. So in terms of the work that's being done in this area, my co-author and the first author on that agenda, Jan, has done a lot of work on sort of improving reward modeling and doing things along the lines of exploring these different approaches in order to come up with algorithms for learning reward models that work better. And that's, I just showed a few examples in this category. So here's an example where instead of saying, let's just have the human give feedback comparing behaviors that the agent is doing, we can also have the human demonstrate some behavior. And then the agent can start off by imitating the human and then only later get the human preferences to distinguish between those behaviors. So I think it's worth now actually me skipping back a tiny bit to this slide and talking about why we can't just do imitation. And the reason is that ultimately we hope to go beyond what humans can do themselves and to be able to teach AI systems to do tasks that we ourselves cannot do. So for instance, in AlphaGo, we were able to teach a Go system to perform at a superhuman level, and it did things that humans never would have chosen to do, like this famous move 37. Now, that was made possible by us having a very clear reward function already because it was a game, and we could just say the reward is to win the game. On the other hand, as soon as you allow for the possibility that the AI can come up with novel solutions that humans wouldn't do, then you also allow for the possibility of novel solutions like this circling boat that are actually not what we want. And so ultimately, we want to expand the space of behaviors that we can train AI systems to do, the kind of tasks that we can train them to do. But we have to be very careful that as we're doing this, we're only getting these kinds of desirable novel solutions and not the undesirable ones. And that comes down to figuring out the right reward function or the right way to learn the reward function and use that learned reward function to train the agent. So the other line of research on reward modeling that I think is important to mention here is applying it to tune these foundation models. And so a lot of the work right now on aligning foundation models is not just using prompting or using fine-tuning with supervised learning. A lot of it uses reinforcement learning from human feedback, which is another term that basically refers to the same thing, reward learning. Now, I mentioned those lines of work because I think they're very important to know about, and they're very active. What I'm working on with my research group is more focused, however, on ways that this approach can fail, and in general, ways that specification can fail. And I focus on this because I think it's a very difficult problem, and I think we need to understand all of the ways that it can go wrong so that we don't put undue trust in an approach that has worked so far for simpler tasks and simpler models. I think as we expand the scope of things that we try to do with AI systems, and as the systems get bigger and smarter, there's the possibility that approaches that have worked in the past will break down. And so I'm very concerned that even though we have seen some promising initial results with reward modeling, I'm concerned that this approach might, in the long run, fail if we don't make sure that we anticipate all of these failures. So what I'm going to do in the remaining about 15 minutes of my talk is tell you about these three different ways that we can have a specification failure that I have studied in these three papers. So these two are with collaborators, including some of my current students. And this last one is work that I did during my PhD and also during my internship at DeepMind with Jan. So at the same time that we were writing this agenda about reward modeling. So again, I think this other work is really promising, really exciting. One of the reasons that I'm focused on the failures is because I think there's already so much work being done in these other areas, and I kind of want to, set myself apart. And I also think, actually, despite all of this work on sort of improving the approach and applying the approach, we still don't have anybody who is focusing on figuring out, is this approach actually going to work? Is it going to work as we scale up? And so that's kind of one of the main focuses of my research right now. So yeah, let's jump right into talking about these papers now. So this is a very recent work that I did with students from Oxford and Mila and one of my students at Cambridge. And the idea here is basically, we're asking this question of, when is it okay to optimize a proxy reward function? So the issue that we saw here with the boat race is that the reward function that was programmed was actually only a proxy for what we really cared about. And in general, when we are programming reward functions, we don't know, it's very difficult, or it can be impossible, to get everything that we care about into the reward function. So this is just a video game, but in the real world, there's all sorts of impacts that an AI system could have. And if we don't account for all of those impacts, then if we don't include them in the reward function, is what I mean by account for them, then the AI system by default won't care about them. And so if it's able to do something to improve its performance, like in this case, even though the boat crashes into the wall and catches on fire, it still gets more points. We might say, oh, actually, we don't want the boat to catch on fire, but that wasn't included in the reward function. And so long as we don't include things like that in the reward function, the reinforcement learning system just won't care about them. So the question here is, when we have a proxy like this that includes some of what we want, but not all of what we want, or maybe it includes all of what we want, but it doesn't appropriately trade off the value of different things, are we going to get acceptable behavior or not? And when we learn a reward function, I think we can only ever expect to learn a proxy. So if we had a human giving the reward, that might be, representative of the human's real preferences or intentions. But when we use human data to learn a reward model, we know that the model is never going to be perfect. So there's always going to be some sort of flaws in the model. And the question is the model good enough, or are those flaws too severe? And so we will see this kind of perverse instantiation, or reward gaming is the term that we use for it. So reward gaming has this signature, appears in this signature way that you can see in these plots. So in black, we have the true reward. And in green here, we have the reward of the proxy, which in this case was a reward model. And you can see most clearly, I think, on this leftmost plot. So these are plots from one of those papers that I showed earlier in the slides, training on Atari video games using reward modeling. And we just show the returns on the y-axis. So higher is better. And as we train the agent, both the proxy reward and the ground truth reward are going up at the beginning of training. But at some point, there's a sudden transition, and the proxy reward continues to increase. And in fact, in this case, it jumps up suddenly, while the real reward drops. And so this is what the sort of characteristic reward gaming learning curves. Your agent is exploiting the difference between the reward model and the real reward, and has found a way to maximize the reward model that doesn't actually give you good reward according to the real reward function that you actually care about. So one of the main contributions of our paper is just to define what it means for two reward functions to be gameable. So when could such a thing happen in principle? And for this to happen, we say we need there to exist a pair of policies such that the returns are lower according to one reward function for the first policy, but higher according to the second reward function. And that means that actually, if J2 was the proxy here, then it would be happy to switch from following pi prime to pi, because that would improve the proxy reward. R2 or J2, the proxy returns. But doing that would also decrease the true reward. And so that would give us this kind of a learning curve. Now, just because there exists a pair of policies that look like this doesn't mean it's guaranteed to happen, but it does mean that it can happen. And so that's basically what we wanted to do, is just define sort of what it means that these reward functions could ever have this happen when we optimize the proxy. And it turns out what this amounts to is saying, if you want to find an ungameable proxy, you're allowed to replace strict inequality in the orderings over policies with equality. So if you think about reward functions actually can order all of the policies according to their returns, which we represent by J here. And in that ordering, if you had the true reward function saying pi prime is better than pi, and you had the proxy reward function saying they're equally good, that actually wouldn't be a problem, because then when you optimize the reward function, there's no pressure to switch to pi from pi prime. And so it's only this case where there's actually an optimization pressure, as we call it, to switch to a policy that is actually worse according to the real reward function, that we say that these reward functions are gameable. And yeah, so I'll move on now. So the results that we had in this paper, let me see how much time I have left. Yeah, good. I'm doing all right for time, so I can tell you a little bit about our results as well. So first, we just had this definition. Then what we want to do is explore the consequences of this definition, and to see, how, because the ultimate question motivating this research was, how good does the proxy need to be in order for us for it to be safe to optimize? And by safe, we mean that we won't ever see this kind of effect where it looks like we're doing better according to the proxy, but in reality, bad things are happening. Maybe even disastrous things are happening. And it turns out that this relationship is entirely trivial if we consider all policies. So there's actually no way to have a proxy that is ungameable unless it's essentially exactly the same as the real reward function. So this is remarkable because it says that actually this approach of learning a proxy reward function might just be doomed in some sense. Now, I don't believe that that's actually true, but I do think that our results should, give some pause. And I'll talk more about the consequences of our results at the end of, in a couple minutes. So one of the implications here is that you might need to restrict the policy set in order to get non-trivial examples of ungameability. And so in particular, so that's what we look at in the next couple of results here. So I should mention as well that this paper is actually entirely theoretical. We're just focused on, as it says in the title, defining and characterizing this notion of gameability. Another thing that we're working on is actually looking at whether this happens in practice, or what factors influence whether or not you will actually get reward gaming. Because as I mentioned, just because the two reward functions are gameable doesn't mean that you will actually see gaming. And excuse me. So once we restrict the policy set and we say maybe we're only going to consider a finite set of possible policies, it turns out that there are always ungameable pairs of reward functions. So these are kind of our main results here. And I think I'll focus on those for now, discussing this work. So I just wanted to give you a little bit of a flavor of the idea behind these proofs. So when you look at the returns of a policy, this is actually linear in what's called the visit count. So just how many times does the agent visit each state and each action? And of course, it's discounted, as always, by gamma in reinforcement learning. And so the returns of a policy can just be given by this inner product between the reward function and the visit counts. And so the implication turns out to be that if you have anywhere in your policy space an open ball, so basically if you have volume somewhere in the space of policies you're considering, then you can always take some visit counts that you get from two different policies that you want to set equal, project them in some sense inside that open ball. And then within that open ball, the only way to set these equal is to flatten the entire reward function so that any visit counts have equal returns. So yeah, so you can basically think of this operation of finding a proxy as based on this thing that I show here. You replace some inequality with equality. So you have two policies, or in this case, the visit counts of those policies that start out proxy that is not gameable. But if you do this within a continuous space, it turns out that that just automatically sets all of the visit counts equal. On the other hand, if we only have a finite set of policies, then we can think of the reward function as this plane that we sort of tilt around in order to try and set two policies equal. And there's a way of doing that when you have a finite set of policies that is guaranteed to exist and give you something where you set two policies equal, but you don't set all the policies equal. So a non-trivial example of ungameability. So just to say a little bit about what we've concluded from this paper. So I think, first of all, this is still really like preliminary in a sense, that I think there's a lot more work to be done on expanding this definition and in general on this question of gameability. But the first thing I think to say is that maybe actually optimizing proxy rewards is not actually the right approach that we should be taking. And then maybe we actually need to think more about alternatives like imitation, even though it has this limitation where we can't exceed human performance, or constraints. Maybe we need to incorporate constraints. But maybe an even more important takeaway is to say, optimizing a proxy, we should think about that always as a heuristic. So anytime we're optimizing something, we shouldn't think that the goal is just to optimize it as well as possible. In the same way that like optimizing for training performance is as well as possible can be a really bad idea because you get overfitting. In general, I think we can never take the specification of the goal so seriously that we think that we should optimize it. Instead, we want to optimize it a little bit, right? Like we want to optimize it to this point and no further. And so there's this challenge of knowing where that point is. Like how much can you trust this reward function? How much can you optimize against it before it starts to peel apart from what you actually want? And once you think about it that way, then this approach to reward modeling should be viewed not as learning a reward function that can be optimized safely, but rather learning a reward function that can be optimized carefully. And if we optimize it carefully, then we can get a good policy out. So the ultimate product that we're trying to produce here will not be the reward function, but only a policy. All right, so I'll talk about this other paper now, which is about goal misgeneralization in deep reinforcement learning. So this is a paper that my student Lauro and these collaborators started before he actually joined my group. But since he joined the group, we did a lot more work to polish it up and submit it to ICML. And so it was accepted at this ICML. And so previously I talked about the idea that your specification can fail if you don't have the right reward function. But it turns out that you can also have an agent that has the wrong intention, even if you have the perfect reward function. And that's the main point of this work. So we use this example of this coin run environment, which is a lot like Super Mario Brothers. The goal of this agent is to get to the end of the level where there's a coin. And in training, in fact, the coin is always at the end of the level. And we give it a reward of 1 when it reaches the coin. But the agent doesn't know if it's getting rewarded for reaching the coin or reaching the end of the level. So what happens when we put the coin somewhere else is that the agent goes to the end of the level and ignores the coin. And so this is a kind of robustness issue that is caused by the agent having the wrong intentions. And in fact, this happened, again, even though we trained it with the right reward function. So the point here is that having the right reward function is actually not enough to get the right behavior. And in fact, it's not even enough to get the agent to try and do what you want. So contrast this kind of failure mode, where the agent is goal-directed and the policy is capable of achieving its goal, in this case of reaching the end of the level, with a more typical kind of failure, which would be a capability failure, where the agent really isn't capable of doing anything sensible. And so when we see that an agent or an AI system isn't doing what we want, a lot of the time we might assume that it's because of this kind of a failure. But in fact, it could be that it's doing the wrong thing, but it's doing it competently. And that could be a bigger issue, because then it could be actively pursuing some goal that is different from what we want. And so one of the main things we did in this work is to formalize the difference between these two kinds of failures. And basically we say, if the agent is still behaving as an agent, but one with the wrong goal, then we would say it's goal misgeneralization. Whereas if it's behaving less like an agent and more like a device, so just a sort of arbitrary policy, and you can look at this paper if you want to read more about where we get this definition, then we would say it's not goal misgeneralization, it's just a regular sort of capability robustness failure. Great. I am close to out of time, but I will go through this work really quickly. So this is the point of this work. So actually, I'll skip to sort of my later conclusions, and then I'll come back and show you something there. So I've talked to you about these two sources of specification failure, and I'm about to say a little bit about this one as well. And I just want to highlight what is causing the failure here. What is causing the agent to have the wrong intention? And in the first case, it's very simple. It's just that the designer didn't provide a good reward function. So the reward function didn't actually express what we want. And as long as that's the case, we might have to worry about reward gaming. That's one of the conclusions from that paper that I talked about. On the other hand, even when you have the right reward function, the agent can implicitly learn a different reward function that is not the one that you intended. And that's the source of the failure in this goal misgeneralization, is that the agent learned to get to the end of the level instead of to pick up the coin. And it learned that because the coin was always at the end of the level in training. Although we have experiments as well where if the coin is almost always at the end of the level, you can still get a similar kind of failure in practice. So the last source of failure that I'll just go into really briefly before wrapping up is nothing to do with like the reward function. I'd like to describe this instead as about the means that the agent uses to optimize the reward function. So I've already talked about the idea that optimizing something really hard is maybe not a good idea. But this is sort of something like that, but a little bit more subtle, where we're saying it's not only an issue of how much you are trying to optimize that thing, it's also a question of how you are trying to optimize it. And in many cases, I think we want to optimize something, but we don't want to optimize it using certain paths of influence. So the example that I like to use for this is content recommendation. So in content recommendation, you want to get the content to match the user's interests. And the kind of solution that we expect, I think, when we phrase the problem that way, is that the user's interests don't change that much. Maybe they change, randomly, or just as a result of that person becoming interested in different things naturally or organically. But the content that we provide is going to match their preferences more and more. On the other hand, when I say get the content to match the user interests, we can also do that by changing the user's interests to match the content. So just saying these two things should match doesn't say, do I want to change the content I'm providing, or do I want to actually influence the user and change what they are interested in? And so you can think of this as basically you're recommending some content, and the user either clicks on that content or not, and the reward is, do they click on it? And just finding good content that matches the user right now is fine. But if you also optimize over the influence that you have on the user, then you might be more likely to come up with solutions that would have a harmful outcome for society, like changing users' interests to be more interested in conspiracy theories or radical politics or other things that might keep them on the platform for longer. And I'll say one more thing about this quickly, which is that one of the really important things about this work is that not trying to influence something is not the same thing as trying not to influence it. And what we're focused on is not trying to influence. So you might indeed change somebody's interests when you interact with them. And that's okay, so long as you aren't trying to influence them. So again, this gets at the intention of the AI system. And unfortunately, I don't have time to walk through these experiments, but you can take a look at the paper or follow up with me if you do that. So just to conclude, I've argued that a key challenge for AI systems is to get them to have the right intentions or motivations. And that this is ultimately really important in order to get the kind of behavior we want. So going back to these definitions of AI alignment as getting the right behavior or getting an AI system that tries to behave in the correct way, I think the second one is in some sense more important, because I think whether or not we get the right behavior from an advanced AI system that is very capable is mostly going to come down to whether or not it understands what we want and is trying to do what we want. And it's my opinion that we need to learn these things, and that manually specifying the intentions or the motivation or the goal for an agent is not going to work. It's not going to be a scalable approach. So somehow we need to figure out how to leverage machine learning for learning the goal that the AI is supposed to optimize. Now, once we look at it that way, it's clear that human feedback is going to become a key bottleneck for doing this. So we're going to have more and more unsupervised data and more computational resources, but we only have a relatively limited amount of human labor that can go into building these systems and to telling them what we want them to do. So, and then finally, I talked about these three different challenges and some of my work on identifying these challenges. And I'm very interested in going beyond this to start addressing these challenges as well. And finally, just a reminder, I'm looking for postdocs, so if any of this was interesting to you, or if you know somebody who would be interested, please put us in touch. And thank you so much for the invitation and for all of your attention, and really looking forward to questions.
Thank you so much, David. It was really a nice talk. I really enjoyed it. And we received quite many questions, actually. They lie on a very wide spectrum, both on the general AI alignment side, language models, etc., and also on the other side of very technical and specific questions on reward modeling. So maybe I'll just alternate between these two types of questions.
Sounds great.
Okay. Yeah. Okay. So the first question is about the claim that you made about the alignment of GPT-3 is the next AlexNet moment. And what advice would you give to an ML student wanting to pivot to AI alignment research at the moment?
Yeah, that's a great question. So I think like one thing that, where to begin? So I think one thing is sort of going back to the analogy with deep learning. I think it's good to think about, not just the next deadline or the next, year or two, but think about like 5 years, 10 years from now, and really try and do research that is going to be impactful on that kind of timescale. So that's I think can be hard to do given the culture of the field is very short-term focused and deadline driven. But I think ultimately this is actually good advice almost no matter what kind of research you're doing. But it's especially important for alignment, I think, because for alignment, we really want solutions that are going to scale. And so you can do a lot of work, and this is important work, on getting AI systems to behave the way you want right now, like in some actual application. And I think that work is very valuable, especially when it's very focused on a particular application and on ensuring that the system behaves reliably and is not harmful to its users or to society. But in the long run, I think there are hard technical challenges, like the ones that I mentioned, that we're only beginning to grapple with. And if we want to be able to continue to get the right behavior out of AI systems in the future, we need to focus on identifying and addressing these fundamental challenges. So these are challenges, like these three that I mentioned, and also just about the limited quantity of human feedback that is going to increasingly be a bottleneck. So that's the first part of my answer. Let me think if I want to say anything more. Okay. Another thing I think is, I think it's very important to think about these problems, think for yourself and think creatively and read a lot about what other people have said and thought and written about these problems. But ultimately, I think everyone who is serious about working on the alignment problem should come up with their own views and their own model for like how the future of AI will look and how we will be able to shape it, or what the challenges will be. So there's a lot of stuff has been written. Much of it is not actually in academic papers, but is on forums like Less Wrong, or is on people's individual blogs. And a lot of that content is like, I think it's important to be aware of. And I think it's a bit of a challenge, but to balance keeping track of this thought that has sort of happened informally or less formally, and also keeping track of developments in the machine learning community. But I think to be really successful in this field, you kind of want to be tracking both of these things. And there's two newsletters that I think are really great for doing this, which are the Alignment newsletter by Rohin Shah and the Machine Learning Safety newsletter by Daniel Hendricks. Yeah, so I'll leave it at that so that we can take more questions.
Sure. Thanks for sharing this. Rohin was also one of our speakers at a previous talk. Yeah.
Yeah.
And a second question would be, you mentioned about the misspecification of goals, like the coin run example. Do you think some reward learning schemes like preference comparisons, etc., will be able to solve these, or do you think these types of human feedback cannot even solve this type of problem?
Yeah, I guess I'm not actually sure how to interpret that question. So if it's about coin run in particular, the kind of failure here is quite easy to solve once we know exactly what's going wrong. We can just train the agent on levels where the coin is not at the end of the level. And as soon as we do that, as long as it's like more than 1% of the levels have the coin in some random location instead of at the end of the level, then the agent learns to find the coin most of the time. So it's more of an issue if you think about, we chose this example in part because it so clearly illustrates the problem. But in reality, this might happen in a subtle way that you can't even detect. So yeah, so I think the question about whether or not human preferences could solve this kind of problem more generally is a good one. I think, it remains to be seen, right? It's research. So I'm like cautiously optimistic about this direction of work, but I tend to be somewhat pessimistic overall because I think it's actually just very difficult technical problems that we're working on. And so I think it will take a long time to make progress on them. Or I guess not to make any progress, but to like get close to like solving them. The important thing I think so if we think about the actual training environment that we used in CoinRun, where the coin was always at the end of the level, then I think there is a version of learning from human preferences or reward modeling that would be able to solve this. But importantly, you would have to get human input, not only on the states that the agent actually encounters, but also on hypothetical states that are different from what it's actually experienced. Because it really needs to know, is it getting reward from the coin or from the end of the level? And if the coin is always at the end of the level, there's just no way to disentangle them. And so one of the papers that I have in the slides, but I didn't actually talk about much, I'll just see if I can find it really quick. Yeah, so this paper, Learning Human Objectives by Evaluating Hypothetical Behavior, is actually doing something like that, where they say, let's let the agent sort of imagine things that might happen and then get human feedback on those. And so in that case, you could have the agent say, well, what if the coin wasn't at the end of the level? I've never seen that, but I can imagine it. And then the human would say, okay, in that case, it's good if you still go to the coin instead of skipping over it and going to the end of the level. So I think that's a way that I can imagine addressing this kind of issue with reward modeling. I hope that got at like the spirit of the question. Otherwise, happy to clarify if I just totally missed or misinterpreted it.
I think you interpreted it correctly. Yeah.
Oh, great.
Thanks for that. And the third question is on the more general side. So someone asked, how should AI research be more integrated with social sciences and philosophical research, just trying to improve so that it can improve the probability that AI development is positive?
Yeah, that is a big question. Excuse me. So I have a few thoughts about that. So I guess where to begin again? One thing would be when we talk about learning from human preferences, there's this assumption, kind of implicit assumption, that the human knows what they want. And I think that's like quite a reasonable and safe assumption, but I think it's not, strictly speaking, true. Like, there's a difference, I think, between what is called often people's revealed preferences, so what they actually choose when presented with different options, versus what they actually value or what they would prefer if they were more reflective about their decisions. And this is something that you can see with issues like addiction, or maybe even in the context of content recommendation or social media, like clickbait. Like, you might click on something that is sort of interesting or appealing to you right now, but if you thought about it more, you'd be like, I actually don't need to learn about this. It's just some celebrity gossip. It's not really helping me achieve my goals, realize my values, have a happy, fulfilling life overall. So I think we do need to be careful about how we involve humans and human decision-making in training AI systems, and that's something that I think there's a lot of work for social scientists to do. I guess another part of this would be, I think we need to study other fields and other, not even just academic fields, but just like communities of people, and how they make decisions, how they manage risk, and how they manage to coordinate and cooperate with each other. So I think AI development, so besides the technical challenges, and I alluded to this at the beginning of the talk, besides the technical challenges, there will be very significant social and like political, geopolitical challenges, I think, with AI development. And one of the things that concerns me the most is the idea that AI developers will just race forward and push for AI progress at the expense of alignment and safety. And I think there will be strong structural incentives for different actors to do that. And this could be for economic reasons. It could also be for geopolitical reasons. And so I think we need to understand, how can we both like reduce those incentives, or sort of create less pressure for rapid development, and get people to appropriately prioritize safety, reliability, alignment. And then also look at sort of the culture and the cultural side of this. So the culture of teams that are developing AI, how can we get people to think seriously about this? And because right now, a lot of people who work on AI sort of come out of a research mindset and have this attitude that like everything that they're doing is sort of just, science, or almost like a sandbox for them to play in to see, cool results and understand things. But these systems are having really big impact on the real world, and that impact is only going to increase. And so I think there's a kind of responsibility that everybody in the entire machine learning research community has, and not just people working on alignment or people focusing on these social problems. Everybody needs to have some appreciation for what we are doing is going to have a really big impact, and we need to think about those impacts. And especially when you look at like an organization that is doing AI development, I think so there's a paper from Tom Dietrich called, I forget the title, but he talks about the idea of highly reliable organizations. So we often think about like reliable AI system as about, how do we make the AI itself reliable? But I think an even bigger part of the picture is how do we make sure that the people and the organization is set up to treat this, with the seriousness and gravity that it deserves. And we see examples of industries or fields that already have that kind of mentality when they're dealing with things like nuclear physics, nuclear weapons, nuclear energy, or also some types of biological research. And I think we're going to need to incorporate some of the lessons from those fields into the way that we do AI development. I think there's also, so when we talk about like cooperation and incentives, I think this naturally brings in like the field of economics, and in particular mechanism design, which is a subfield of game theory that's often called like inverse game theory. So this is about how do we set the rules of the game so that when the players play the game, it results in a good outcome. And good outcome here usually means like good for everyone, good for society, good on like a social scale. And I think that's an area that I think is very interesting to think about in terms of, yeah, having more cooperative AI development. And I guess I'll leave it at that again, in the interest of time.
Sure. Thanks for elaborating so much on this. And we have our next technical question on reward learning. So someone raised the question that in reward learning, there are many different sources or modalities of human feedback, like preference comparisons, etc. And he or she is interested in your vision about how to use these more efficiently, and also how do we scale up the human supervision or other alignment approaches?
Yeah, that's another great question. So one of the basic results that I think is, I wouldn't say it's super well established, but it makes sense, and it's been fairly consistent with what we've seen so far in the research on this, is that both demonstrations and preference comparisons are really important. And a lot of the time, you can't get to the point where the AI system is doing anything sensible in the first place if it hasn't been trained on some amount of human demonstrations. Excuse me. So there's, for excuse me, for this paper, this is what they did. They pre-trained on human demonstrations, and then they fine-tuned with reward preferences and found that that was much more effective. In some of the empirical work that I alluded to that we're doing in my group right now on reward hacking and reward modeling, sorry, I said reward hacking, that's another word for reward gaming. In some of this empirical work, we're finding something similar where, typically in reinforcement learning, agents start out doing kind of random things that aren't very sensible. And it can take a lot of work, and including potentially a lot of human feedback, in order to get them to a place where they're doing something sensible in the first place. So I think there's a pretty clear and established role for demonstrations and preference comparisons in that sense. In terms of scaling this to other kinds of feedback, so one of the coolest works that I've seen in this area is called, okay, again, I don't remember the title exactly, but the idea is called reward sketches. And what they got people to do is to just watch an entire episode of the agent's behavior and sort of trace out how high or low the reward was at every time step. And of course, when you do that, you're not going to get like very precise numbers, but you will get a good sense of like, oh, it was doing good stuff here, and then this was okay, and then that was really bad, and so on. And that gives you just a lot more data in a sense, because a human can draw a line like that in a couple seconds, but then you get like a data point for every single time step along that trajectory. I think one of the things that is really interesting to me here that I think we're only just beginning to see some work on, and I'm not sure if it will pan out, but I think it will be very powerful if it does, is to use natural language feedback. And so there's been a lot of work on incorporating natural language into reinforcement learning somehow. Usually, though, it's as context and not as feedback. So this is the difference between like something being an input and something being a target, basically. And so you can have the reward function depend on some natural language instruction, and that becomes very similar actually to another slide here. So the stuff that I was talking about like fine-tuning with instructions. But again, that's still using the natural language as input instead of as feedback. But if you think about how we teach other people to do something or what we want or some new concept, it's just so much natural language, and this is so much richer than reward as a kind of feedback. So you can imagine like trying to learn, how to do calculus by just like moving your pen, and someone either like rewards you or not. So like maybe they shock you when you draw the wrong symbol, and they give you some treat if you draw the right symbol or something. It'd basically be impossible to learn calculus that way. But a lot of what we're doing when we train AI systems is sort of like that. And so I think, given that we have these systems that seem to have a good understanding of natural language, it might be possible to leverage that to interpret more rich human feedback, like, oh, you made a mistake on this line because you aren't actually allowed to change the order of integration in this case because, et cetera. And have a system actually understand that and adapt its behavior appropriately. So that's something that I think is very promising. And at the same time, I want to just always like warn and advise caution, because I think it's hard for me to imagine that we would have great confidence that the system actually understands natural language. So when we do something like reward feedback, there's a shared semantics of the reward between the human and the agent, sort of by default, because it's just a number, and humans and AI systems both understand numbers. And we're getting these AI systems that like understand language quite well, but I think there's still compelling evidence that they don't understand it the same way that humans do, and there's still discrepancies. And I know a lot of people these days think that this is a problem that's going to go away as we scale these systems up, but I'm concerned that it won't ever fully go away. And so there's going to be a bit of a, I don't know if you have this expression actually, but like chicken and egg problem. Like you can't solve this problem without solving this problem, but you can't solve this problem without solving that problem. I think there's going to be a little bit of that dynamic with using language for as something like a reward signal. Because if the AI doesn't understand the language perfectly, then your feedback might be misinterpreted, and you might end up again with like the wrong reward function or encouraging behavior that you want to discourage.
Yeah, that's very interesting. Thanks for sharing this. And we have our final question from the audience. How do you evaluate the possibility of AI working on a better goal-setting agenda than humans would do in a similar situation?
I don't understand this question, unfortunately.
Okay, so my personal interpretation is like, under the same situation, do you think it is possible that an AI will set a better goal than humans?
Oh, okay. Yeah. Yeah, I mean, that's another big question. I think like the short answer is yes, absolutely, of course, because humans make mistakes all the time. And not only do humans make mistakes, but there are also humans that are just, you know, don't have good intentions in the first place. So um, yeah, but I think like I'm very skeptical of the idea that like we should pursue that direction right now of like AI systems defining the goal instead of humans defining the goal. To me, that just seems like a recipe for disaster to some extent. I think we can use AI systems to help us clarify our goals, and um, and I think that needs to be done very carefully. But I think for the most part, we should always think about the goal as being coming from the human somehow for the time being. Um, and yeah, so I think like at the same time, there are things that you could do, like maybe in very specific or narrow contexts, it makes sense to have the AI define the goal, and then a human like look at that and say, yes, that is a good goal. So I talked about mechanism design before. And so defining the rules of the game. You can imagine building an AI system that says, oh, here's the rules that I think we should use for, let's say, self-driving cars in order to have a good transportation system based on self-driving cars. And I think, that's the sort of thing where, in some sense, that's defining the goal. That's defining, the rules, but maybe also like how, what the goals will be of the different driving algorithms in that context. Um, and I think that could be, a sensible thing to do. I just think we have to be very careful about it. And ideally, we want to make sure that humans are still involved in looking at that description of the goal and saying, yes, I agree with that. That makes sense to me. I understand it. And I think it will work.